Let's better explain interference with a couple of examples, and hopefully this helps it make a little more sense. We have two transverse waves, A and B, meet and interfere. Wave A has an amplitude of 1 centimeter and a wavelength of 4 centimeters. Wave B has an amplitude of 3 centimeters and a wavelength of 4 centimeters. In these graphs, so in this problem, I'm going to use red for, let's make wave A this pink or red color, and let's make wave B blue. So if we're sketching both waves, the first one is wave A has an amplitude of 1 centimeter and a wavelength of 4 centimeters. That means the wavelength is going to go all the way through 1, 2, 3, 4 centimeters. And its highest and lowest points are going, that would look with a wave of something like that. It goes over 4 centimeters and its amplitude or distance, highest point from equilibrium is 1 centimeter. If we do wave B, which has an amplitude of 3 centimeters and a wavelength of 4 centimeters, it's going to go to the same point, or it's going to have the same 4 centimeter wavelength, but it's going to go higher. It's going to go 1, 2, 3 centimeters away. Its amplitude is going to be 3 centimeters. It's going to come back, and it's going to be 3 in phase. That means they're in the same line with each other. So when we get a resultant wave, when they overlap, your new amplitude is going to be plus your amplitude of the second wave. So the purple of the pink and the blue waves, constructive interference. The next example wants us to look as if we have destructive interference. The next example, we're going to have destructive interference. They're going to be out of phase with each other. So again, if I sketch both waves, the first line, or wave A, is an amplitude of 1 centimeters and a wavelength of 4 centimeters. So that's going to almost look the same. It's going to go 4 centimeters from one end to the other, and its amplitude, its highest point is going to be 1 centimeter, and its lowest point is going to be 1 centimeter. Now is where the difference comes in. When we're drawing wave B, we also are going to still have an amplitude of 3 centimeters and a wavelength of 4, but they're out of phase. When wave 1 is up, wave 2 is going to be down. And when wave 1 is down, wave 2 is going to be up. So where they were up here, they were constructive, they were in phase, they were adding in the same direction. Now they're opposite. So our new amplitude is going to be equal to our first amplitude, or amplitude of the first wave, 1 centimeter, plus the amplitude of the second wave, which is down, so it's going to be negative 3 centimeters. 1 plus negative 3 is going to give us an amplitude of negative 2 centimeters. Meaning our resultant wave is going to have an amplitude of negative 2 centimeters. It's still going to go over a 4 centimeter wavelength, but its amplitude is negative 2. So you can see constructive means that you're going to get a bigger amplitude in your wavelength. Destructive means that they're going to almost cancel each other out, and you're going to get a smaller wave. when you combine them together. So another thing that we can use interference and reflection for is to find what we call standing waves. So standing waves are a wave with stationary nodes. So what a standing wave is, or how it's produced, is when you have your wavelength here, and if you think about this girl, maybe she has a big skipping rope that you would do double dutch with or something, I don't know. Where she's holding it, that's going to be at a node. Where this stays in the middle, that's also going to be a node or null point, and we are also going to have one at our rigid point there, or at our fixed point. So when she starts moving this up and down, propagating up and down, the motion of the wave is going to head towards the wall. So as it does that, your waves are going to be in phase. They're going to go until they hit that rigid point. Once they hit that rigid point, they're going to come back. But remember, your reflected wave is going to be inverted. That means that you're going to be perfectly out of phase. And each of these waves are going to be canceling each other out. She's going to continue to be moving an incident wave towards the wall, and the reflected wave, as it comes back, is going to have an amplitude that cancels each other out. That's going to leave you with a rope that looks flat. But once that reflected wave gets back, she's going to still have her incident wave, and the next reflected wave is going to come back in phase. So as it comes back in phase, now your rope is going to be going the other way. When this happens in real life, it looks like this point, this node, doesn't move at all. But this beginning amplitude is going to go up, it's going to come back down, and then go all the way to the bottom. Then it's going to come back up and up. It's going to be the opposite on the other side of the node. Your wave's going to go down as your first one goes up, or your first crest goes up, and then it's going to come back to the middle. They're going to cancel each other out at equilibrium. Then it's going to continue going up while the other wave goes down. And it looks like you have two waves going up and down with these 3 points staying stationary. So what's happening here again is it goes in phase, it reflects out of phase, then you're in phase again. And that's going to give you this motion that you got these two vibrating waves. So for a standing wave to occur, the waves must be traveling in opposite directions. They must have the same wavelength and the same amplitude. That is very important for a wavelength to happen, for a standing wave to happen. When it's in phase, the crest and the crest or trough, when crest and crest or troughs and troughs occupy the same point in the median, you get constructive interference, like we said before. This amplitude of the standing wave is double the amplitude of the individual waves, and you're going to produce antinodes. So if these stationary parts, or these parts that stay at equilibrium, are nodes, the antinodes are going to be when you're at the highest point or the lowest point. You have your waves below adding together to be double the height, both up and down. When they are out of phase, the crest and the trough occupy the same point in the medium, and you get destructive interference. That means the amplitude of the standing wave is 0 and you produce nodes. Or they are going to cancel each other out. Your amplitude up is going to be the same as your amplitude down, and you're going to be balanced at 0, at equilibrium, the whole way through. So to draw a standing wave, you want to always start on a node. Always start on a node. You can have the whole or half wavelengths if you start on a node. So it makes it a lot easier to solve the problems. You can have whole or half wavelengths. So if we solve an example here, we are given standing waves are set up in a string by a source vibrating at 126 hertz. 7 nodes are counted in a distance of 63 centimeters. So what is the wavelength of the waves traveling in the string? So in this problem, we are dealing with standing waves. But instead of just having the 3 points for the nodes, we're going to have 7. There's 7 nodes counted. So that's 1, 2, 3, 4, 5, 6, 7. And each node is going to be half of a wavelength. So we're going to draw our wavelength going through each of the nodes. Alright, that means that every second node is 1 wavelength. So we're going to have 1, 2, 3 wavelengths in this problem. Those 3 wavelengths are going to be counted up to a distance of 63 centimeters, or 0.63 meters. That means 1 wavelength, if we divide both sides by 3, is going to be 0.21 meters. So what is the wavelength of each wave traveling in the string? Each wavelength is 0.21 meters. What is the speed of these waves? Using our universal wave equation, velocity is equal to wavelength times frequency. That's equal to our wavelength we just found of 0.21 meters times our frequency, 126 hertz. That's going to equal 26.5 meters per second. Let's do one more example with standing waves. In this example, standing waves are set up in a string by a source vibrating at 126 hertz. 7 antinodes are counted in a distance of 63 centimeters. So at first glance, this almost looks like the same question. But what's different is now we have antinodes, not nodes. So when we're drawing this, again, we're going to start at a node, but we're going to have 7 antinodes, which means we're going to have 1, 2, 3, 4, 5, 6, 7. And you're going to end on a node. So our wave is going to look like we go through 1, 2, 3, 4, 5, 6, 7 antinodes. Our wavelength is going to look different from our first equation. So what is the wavelength of the waves traveling in the string? In this case, we have 1, 2, 3 and a half wavelengths. So our wavelength, 3.5 wavelength, is equal to our distance of the rope, 63 centimeters, or 0.63 meters. To solve for one wavelength, we're going to divide both sides by 3.5. And our wavelength of the waves traveling in the string are 0.18 meters this time. So what is the speed of these waves? To figure out the speed, we're going to again use our universal wave equation. Speed is equal to wavelength times frequency. Our wavelength is 0.18 meters. And our frequency is 126 hertz. This gives us a speed of 22.7 meters per second.